video, I'll explain different RAID levels. In the table, we are having different levels like RAID 0 to nested RAID with a brief description. RAID 0 is nothing but stripped array with no fault tolerance. RAID 1 is disk mirroring. RAID 3 is parallel access array with dedicated parity disk. RAID 4 is stripped array with independent disk and a dedicated parity disk. RAID 5 is stripped array with independent disk and distributed parity. RAID 6 is stripped array with independent disk and dual distributed parity. And the last one is nested RAID, is combination of RAID 1 and 0. So first we'll take RAID 0. In a RAID 0 configuration, the data is stripped across the HDD in a RAID set. It utilizes the full storage capacity by distributing strips of data over multiple HDDs in a RAID set. To read data, all strips are put back together by the controller. So here we can observe that we are having the data from the host are A, B, C, D and E. The RAID controller will receive those data and it will strip the data into A1, A2, A3, A4, A5 of block A. Similarly, B1, B2, B3, B4, B5 of block B and so on. And the data is stripped across the different blocks. While performing read operation, we can stripwise. The user can perform the read operation. Suppose the entire block A information need to be read out. At that instant, A1, A2, A3, A4 and A5 are combined together to get back the original block A data. And while reading the information, the blocks are combined together, and the entire block can be read out from by the user. When the number of drives in an array increases, the performance improves because more data can be read or written simultaneously. RAID 0 is used in applications that need high I/O throughput. However, if this application requires high availability, RAID 0 does not provide data protection and availability in the event of drive failure. The major drawback of RAID 0 is it does not provide data protection. Next is RAID 1. A RAID 1 group consists of at least 2 HDDs. So that is nothing but mirroring concept. As explained in mirroring, every write is written to both the disk, that is actual disk, as well as the mirror disk. In the event of disk failure, the impact on data recovery is the least among all RAID implementations. Why? Because the RAID controller can use the mirror disk to recover the data. RAID 1 is suitable for application that requires high availability of the data. So here we can observe that the data from the host are like A, B, C, D till J. The RAID controller will receive those set of blocks of data, and we are having the actual disk like this is disk 1 with the with the data blocks A, B, C, D and E. And similarly, the same set of data blocks are mirrored on the mirror disk. Similarly, the next blocks, that is F, G, H, I, J. So this is the actual data blocks and that is mirrored on the mirrored set. But while performing read operation, the user is allowed to access the original disk as well as mirror disk. But while performing write operation, any modification comes with respect to any of these blocks, data blocks, the respective block need to be modified on the original disk as well as mirror disk. So while performing write operation, so we have to pay the penalty. So next comes nested RAID. Most data centers require data redundancy and performance from their RAID arrays. RAID 0 plus 1 and RAID 1 plus 0 combine the performance benefits of RAID 0 with the redundancy and benefits of RAID 1. This uses stripping and mirroring concept, and it will combine the advantage of stripping as well as mirroring. These types of RAID requires an even number of disks. The minimum number of disks are nothing but 4. RAID 10 is also known as RAID 10 and RAID 1 bar 0. Similarly, 01 is known as RAID 01 or 0 bar 1. RAID 10 performs well for workload that use small random write incentive IOs. So here we can observe that RAID 1 plus 0, initially the stripping is done, after that mirroring is done. So the data from the host like A, B, C, D is received, and the data is stripped. The data can be stripped like A1, A2, A3, and B1, B2, B3, C1, C2, C3, and D1, D2, D3, E1, E2, E3. And after that mirroring is done. So A1 is mirrored over here, B1 is mirrored over here, C1, C1, D1, D1, and so on. So in the case of RAID 10, stripping is done first and later mirroring will be considered. Similarly, the reverse operation is RAID 0 plus 1. So here mirroring will be done first, later stripping concept will be considered. RAID 3 strips data for high performance and uses parity for improved fault tolerance. So here we can observe that we are having the data from the host like A, B, C, D and E, and we store the data like A1, B1, C1, D1 and E1, A2 here, A3 here, A4 here. So for I will take this as disk A, disk B and disk C and disk D, disk C. So here what exactly the RAID 3 does is, so it will compute the parity of entire data within disk A, and that parity is called as AP. So that parity is stored on the parity disk. Similarly, BP, CP, DP, EP and so on. So the parity of individual disk will be computed and that parity is stored on the parity disk. Suppose if this disk is failed to perform, so at that time the data can be reconstructed by considering the parity value. Usually the parity value can be computed using XOR operation, and suppose the RAID 3 will fail only if the actual disk as well as parity disk, both the disks are failed to provide the service. That means, so we are not having our data as well as we are not having our parity. So we cannot reconstruct the actual data. So next is RAID 4. Data is stripped across all disks except the parity disk in the array. Parity information is stored on a dedicated disk so that the data can be rebuilt if a drive fails. Stripping is done at the block level. Unlike RAID 3, RAID data disk in RAID 4 can be accessed independently. RAID 3 and RAID 4 concept is same, but the major advantage adapted in RAID 4 is nothing but, in the case of RAID 4, it can be accessed independently. The data disk can be accessed independently, so that specific data elements can be read or written on a single disk without read or write on the entire strip. RAID 4 provides good read throughput and reasonable write throughput. Next is RAID 5. In the case of RAID 5, we are using distributed parity. So what is the meaning of distributed parity? The parity will be stored on the other disk. So we are not using dedicated parity disk to store the parity value. Here what exactly the RAID controller does is, so it will take the data from the host like A, B, C, D and E. It will strip the data across different disks. So like A1, A2, A3 and A4, and this block parity will be computed, that is called as, if this is disk A, B, C and D. So AP will be computed, which is stored on the last disk. Similarly, the BP is stored on the fourth disk, CP is stored on the third disk and DP is stored on the second and EP is stored on the last. Suppose here what happens is, if you are having, if disk and this disk is failed, so disk A as well as disk B is failed. So at that instant the disk A can be reconstructed by considering the parity AP, and disk B can be reconstructed by considering the parity value BP, and the parity of DP and EP can be computed by considering the actual data which is present on disk D as well as disk E. So but suppose any more than 2 disks are failed, in such instance we cannot recover the data. So if this and this disk is failed, we can somehow manage the data recovery, or we can overcome from the disaster by taking the parity value as well as the actual data value. But if more than 3 disks are failed, in such instant we cannot recover or reconstruct our data. In RAID 5, parity is distributed across all disks. The distribution of parity in RAID 5 overcomes the write bottleneck. RAID 5 is preferred for data mining, medium performance media surviving, and relational database management system implementations in which database administrators optimize data access. Next is RAID 6. RAID 6 distribute the parity across all the disks. The write penalty in RAID 6 is more than that in RAID 5. Therefore, RAID 5 writes performance is better than RAID 6. To rebuild operations in RAID 6 may take longer than that in RAID 5 due to presence of 2 parity sets. So we are using double parity value. So that means we will compute, for single disk we will compute 2 parity. So for example, AP and AQ for disk A, BP and BQ for disk B, CP and CQ for disk C, DP and DQ for disk D, as well as EP and EQ for disk E. So here I can observe that we are having the data is stripped across different disks over here, and A1, B1, C1 and DP, that is nothing but parity of disk D, and EQ is the duplicate parity of disk E. So here, if suppose I will take one case, disk A is failed, disk B is also failed, disk C is also failed. So disk A value can be reconstructed using the parity value AP. Disk B is failed, so its parity is stored over this one. So I can reconstruct this, as well as disk C is failed, its parity is stored on which disk? The disk CQ we cannot reconstruct. So we are having here AP, PQ, C2, D3, E3 and AQ, C3, D3, EP. So we cannot reconstruct this particular disk.